Welcome back, everyone. We have with us Ajay Nair from the Indian Institute of Science, Bengaluru, and he will be speaking on the Goldman bracket characterizes the homeomorphisms between non-compact surfaces. Yeah, over to you, Ajay.
Hi. Yeah. Hi, everyone. Thank you. Thank Soumya for considering me and giving me this opportunity. Let's start. So this is a joint work with Shumanto and Siddhartha Gadgil. The title of my talk is the Goldman bracket characterizes the homeomorphisms between non-compact surfaces. So it's an age-old question of uh, when is homotopy equivalence a homeomorphism? Oh, I'm sorry. So we will be tackling that question. So let's start with basics. So what is a surface? The surface is a two-dimensional manifold, and closed surface is a compact two-dimensional manifold, and a surface with boundary is a two-dimensional manifold with some charts into closure. So we all know examples. So this is, for example, a closed surface, and this is, for example, a surface with boundary because the charts here go into half plane, right? And so then we get to a very famous theorem, Dane-Nielsen-Baer theorem. So if you take two closed surfaces, any homotopy equivalence between them is homotopic to a homeomorph. So this is a very classical theorem. So as we have already seen the definitions of mapping class group, this also says this, that
What is 5 year? Uh,
it's a homotopy equivalent. It's a
Oh.
continuous map, which continuous map which has an homotopy.
okay. Phi is homotopy. Okay.
Yeah, any homotopy equivalence phi is homotopic to a homotopy. Yeah. So we have close. So this can be also. So there are many ways to state this theorem. So this can be also seen as. This can be also thought of as this. This another way of stating a Dane-Nielsen-Baer theorem, that is mapping class group. So given any mapping class group element, you have a map into outer automorphisms of the fundamental. So what are outer automorphisms? It is just automorphisms up to conjugation, that is quotiented by inner automorphism. So you take. So what does this signify? I'm also taking orientation reversing. I'm also taking orientation reversing homeomorphisms. So yeah, I mean that is another way. But let's take this as a statement for Dane-Nielsen-Baer. Now a natural question is to ask what happens if instead of closed surfaces, you ask the same question for compact surfaces with bound. Is it homotopic to any homotopy equivalence? Is it homotopic to homeomorphism? And the answer is no. It is not true because the examples, like if you take one whole torus, right, and if you take a pair of pans, right, or maybe a better way of seeing this is you think of this as the pair of pans. So this is your surface. So and look at this subspace. So this deformation retracts onto this, and also one whole torus deformation retracts onto this, and they basically the deformation retract onto the same wedge of two circles, right? So they are homotopy equivalent, but clearly they are not homeomorphic because one whole torus has a genus, right? So this is not true for compact surfaces with boundary. So is there any condition that you can put such that you can characterize? Is there a way to characterize homeomorphism? So this is a theorem by Siddhartha Gadgil that if you have compact surfaces with boundary, a homotopy equivalence between two compact surfaces with boundary is homotopic to homeomorphism if and only if it preserves the Goldman bracket. Right? So there is this algebraic object called Goldman bracket, and if your homotopy equivalence preserves this Goldman bracket, then you can say that it can be homotope to a homeomorphism. Right, and so now let's see what the Goldman bracket is. So it is a bilinear map from Z algebra generated by free homotopic class of closed surface to itself. So there are many things here. So first of all, what is a free homotopic class of closed surface, and then we'll also look at what this summation exactly means. There are many terms which are not clear. So I'll define them one by one. And this summation is over the set of intersection points of alpha and beta. So alpha and beta are two, think of alpha and beta as two curves, and then they'll intersect at finitely many points. And then your summation is over these points. And assume the intersections are transversal and everything is in general. You can always assume that. So what are free homotopy classes? So we know what a fundamental group is. If then there the homotopy is fixing a base point. Free homotopy class is something that doesn't fix a that you look at the curves without fixing the base point. So let's say this curve and this curve, these are homotopy equivalent, but this curve and this curve, sorry, these are free homotopic, but this curve and this curve are not free homotopic, right? And you look at the set of, so yeah, I mean, basically alpha from S1 to sigma, beta from S1 to sigma, these are homotopic, these are freely homotopic if they are freely homotopic as maps. Alpha is homotopic to beta as map, right? And there is no base point being fixed. And free homotopy classes are actually same as conjugacy classes in the fundamental. Conjugacy classes of the fundamental group. That is, every free homotopy class is given by a conjugacy class of the fundamental. Yeah, these are all not very difficult to see because changing a base point is just conjugating by a path. One way to think of it is that, right? So these are the free homotopy classes. And what is a Z algebra generated by set of free homotopy classes? Is just you take the linear combinations, formal sums with this set of closed curves, the set of free homotopy classes as a basis, right? And the next part is this. For this, I would need color. Just a second. Does anyone know how to hide this? Okay.
Hide what?
I have this top panel, right, of
Pens.
options.
The colors?
No, I don't see the pens. I see the zoom options. I just wanted to close that, but
maybe
yeah, it's gone. Thank you. Yeah. I got it. Yeah. Okay. So yeah. So now I'll define what this is. So let's say if I have this, let's say I have this curve, right? And I have, let's say, this curve. Now this is the intersection point between these two curves. Now I just give some orientation on these curves. Right? These can be oriented. But okay, so before starting, I have an oriented surface. So this is surface with a prescribed orientation, so with an orientation, right? So what is alpha star pi? So this is pi. What is alpha star pi beta? Is just the concatenation of those two curves. Concatenation of those two oriented curves. That is basically this would be. Oh, sorry. Okay, let me draw another diagram. So basically, this is, you start from here, you go around alpha, and then you go around beta. So this is my alpha star pi beta, right?
You want this to be simple?
No. Yeah, I'll mostly draw simple curves, but yeah, but it is I don't want them to be simple. Yeah, it's just so it is clear that this will again be an element of some free homotopy class, right? You're just concatenating and then taking its free homotopy class. So this will again be an element of free homotopy class. Yeah. So what is the definition of Goldman bracket? You take alpha and beta, right? And you look at all the intersection points, and then you concatenate alpha and beta at all the intersection points, and then you sum it over those with an extra coefficient. And what is this? Epsilon pi is either 1 or minus 1. So epsilon pi belongs to +1 or -1, depending on the orientation generated at this intersection point. So at this intersection point, you have one strand like this and one strand like this. So at this point, these two strands give a basis of the tangent space of the surface, right? And we already have a fixed orientation. So we just check whether this orientation, the orientation given by this basis, matches with the orientation we have fixed. So if it matches, it's +1. If it doesn't, it's -1. Right? So this is Goldman bracket. So you need orientation to define Goldman. Yeah. So this is how you define Goldman bracket. So you take any two homotopy of closed curves, and you take representatives. You look at the intersection points, and then and this is how you define. Okay. So so this is well defined. That is, it depends only on the free homotopy class, not the representatives you take. This was proved by Goldman, as the name suggests. So let's see some properties of Goldman. So the Goldman bracket is a well-defined bilinear map. It makes sense over homotopy classes, because that definition seemed to be being defined on representatives, but it makes sense over homotopy classes, and it's skew symmetric. That if you should, that is easy to see, right? Because the only difference, the concatenations wouldn't be much different. The only difference would be the that epsilon pi's just get flipped, and then it satisfies Jacobi identity. So this is
I have a question.
Sure.
In the above page, you have drawn two curves, a direction of two curves, plus sign, like a
yes.
So how it is come? Is it something like derivative of the curves?
Yeah. So you just look at this point. This curve will have a tangent vector, right? And this curve will also have a tangent vector. These two vectors, as the intersection is transverse, these two vectors should form a basis for the tangent vector of the surface, the tangent space of the surface, right? And you already have a fixed basis on the surface because you have an orientation. You just check whether it matches or not.
Okay.
Thank you. So these are the properties of the Goldman bracket. It's skew symmetric. It satisfies Jacobi identity. So this basically gives a Lie algebra structure on this Z algebra generated by free homotopy class of closed curve. So I'll not be proving all this. So the main interesting property that Goldman proved is this fourth property that I have kept it in a red box. So if you take if you have a free homotopy class which has a simple closed representative, right? Not all free homotopy classes will have simple closed representative, right? Like for example, this one, you cannot make it into a simple closed curve by any free homotopy. So let's say if alpha has a simple closed representative, then for beta, which can be closed, if the Goldman bracket is 0, if and only if beta intersection alpha is null. That is, if you have a simple closed curve and any curve which has Goldman bracket 0 with that simple closed curve is actually disjoint from that. Right. The other direction is easy to see. If you have two curves which are disjoint, then the Goldman bracket is 0 because there are no intersection points. It is 0 because you are summing over a null. Right. So if they are disjoint, it is easy to see that the Goldman bracket is 0. But the converse is true only if one of them is simple. That's what this says. So now an important lemma. So for a compact surface with boundary, a non-trivial curve alpha is peripheral if and only if the Goldman bracket is 0 for every curve in the free homotopy. So it's in peripheral structure. So it in some sense preserves peripheral structure. That is what this says. So if you have a non-trivial curve on a compact surface with boundary, and if it is the Goldman bracket with it is 0, it basically doesn't Wait, what am I saying? Okay, yeah. Let me be more clear. That is, so if I have alpha such that alpha beta is 0, that alpha beta is 0 for all beta in phi hat s. So in particular, it is 0 for all beta simple closed. In particular, this is true. So that would imply that alpha is disjoint with beta for every beta simple closed. If it is disjoint from every simple closed curve, then it is easy to see that it will be on the boundary, right? So if you have some compact surface with boundary like this, we have some genus, and this curve is disjoint with every simple closed curve, right? Then it has to be to the periphery. It has to be one of the peripheral curves. That's what this lemma says, right? Then I hope things are clear till here. So so Goldman bracket is this algebraic structure on the Z algebra generated by free homotopy class of closed surfaces, closed curves, and preservance of these structure for compact surfaces with boundary actually tells that the homotopy equivalence is homotopic to homotopy. Now let's define what infinite type surfaces are. Surfaces, infinite type surfaces are surfaces with infinitely generated fundamental surfaces. So for example, this is called a Loch Ness monster. It has infinite genus going in one direction. This is called Jacob's ladder. It has two ends because you could see there are two infinities in some sense. And then this is the most generic, how a generic infinite type surfaces would look like. So you think of this as some Cantor tree, thickened Cantor tree. So this structure is repeating infinite, and you could have genie that. So this is how complicated a non-compact surface can be. Right? This is an example of a generic non-compact surface. Yeah. So let's go ahead. Yeah. So this is our theorem. So if you take two non-compact surfaces without boundary, and if it is not homeomorphic to plane or cylinder, then a homotopy equivalence, you need a oriented. So, and a homotopy equivalence is homotopic to an orientation preserving homeomorphism if and only if it preserves the Goldman bracket. So our theorem says that it is, so the theorem for compact surfaces with boundary also follows for non-compact oriented surface without boundary. So Goldman bracket determines and characterizes the homeomorphism. Yeah, so I'll just give an idea of the proof. So we make an important reduction. So this is the theorem by Sumanta. So if sigma prime and sigma are non-compact surfaces without boundary, and if it is not homeomorphic to plane or cylinder, so a homotopy equivalence is properly homotopic, is homotopic to homeomorphism if it is proper. So if you have a proper map, if you know that your homotopy equivalence is a proper map, then it is homotopic to homeomorphism, right? I think I don't have to define what proper map is. Just quickly, proper means F inverse of K is compact for every K compact, right? But the best way to think about proper maps is if you are going to infinity in the domain, you're also going to infinity in the codomain, right? If infinities go to infinity, nothing, things will not stop at a bounded place. So yeah, so therefore, so by this reduction, to prove our theorem, it is enough to prove that if F preserves the Goldman bracket, then it is actually homotopic to a proper map. Then you would have a homotopy equivalence homotopic to a proper map. So then it has to be homotopic to homeomorphism. So the only thing we have to prove now is that if you have a homotopy equivalence that preserves the Goldman bracket, it is actually homotopic to a proper map. I hope this reduction is clear. Okay, so I just give a quick outline of the proof. So what you do is exactly you take, so just to be clear, so sigma is my codomain, sigma prime is my domain. So we take an exhaustion by subsurfaces of sigma, and then we construct an exhaustion by subsurfaces of sigma prime, and also together we construct some maps gi from ki prime to sigma such that Gi is homotopic to F restricted to Ki prime, and Gi plus 1, and this Gi plus 1s are extensions of Gi into the next subsurface in the exhaustion. And so this is the important property which gives you the essence that yeah, I mean, this is why because we want to construct a proper map, this property is what gives us that final result. So yeah, so Gn of Kn prime minus Ki prime is subset of sigma minus Ki. So that is so yeah, let me just draw it here. So if you have Ki prime like this, and if you have Kn prime like this, so this one is Kn prime, and this is Ki prime. So this part is mapped to some part outside Ki. And now as the Ki's are getting bigger, these will also get like bigger, and then farther things are going to farther. That is what this final property says. So yeah, so and then the limit of this Gi will give us the final. Is this clear? Okay. So yeah, so this is the outline. So I'll just give quick review of each steps. So how do I construct the exhaustion? So first I have an exhaustion K1 subset K2 of the surface sigma, that is the codomain, and I'll take a filling alpha I. So let's fix K1. So I take a so let alpha I be a filling system for K1, right? And then this would imply there exists alpha I prime such that F star of alpha I prime is equal to alpha I. This is just because F is a homotopy equivalence. Now you take the subsurface which contains all alpha I prime to be K1. So I'm just pushing some things under the I'm hiding few things here. I'm not completely giving you the details, but this is what the sketch is. So now you take a filling system on the right hand side, and you take the inverse image, homotopy inverse of this filling system, and then you construct K1, right? And right, and you can actually construct K1 prime such that every connected component of sigma prime minus K1 prime is non-compact, and they intersect K1 prime on a single boundary component. So they would basically look like this. So there will be non-compact components like this. So these are non-compact components. This is my K1 prime. So I mean every Ki prime. And yeah, and they are all only intersecting at one boundary component. Yeah. So this is how this. So I'm just saying that I'm constructing K1 prime, but this is how I construct every Ki. Right. So I got a exhaustion for K1 prime. Now how would I construct the first map? That is G1 from K1 prime to sigma. So first thing to note is that if I have any surface with boundary, I'll have a graph on which it deform retracts to. It will deform retract to this graph, right? If you have a surface with boundary, there is a graph on which it deform retracts. So let's call that graph gamma prime. So Right. So now let's say gamma prime. Sorry, I should have written it the other way. K1 prime def retracts to gamma prime. And so now you have f from gamma prime to sigma, which is just restriction of f. And then you have a neighborhood of gamma prime, which also deformation retraction into gamma prime. And then sigma, let's call this deformation retraction rho. And then you have this f. So now you define your G1 restricted to this neighborhood to be f composed rho. Right? So it's easy to see that G1 is homotopic to f because they generate the same homomorphism at the level of fundamental groups. And now you can extend the remaining, so whatever is remaining, so if you just remove from K1 prime the neighborhood of gamma prime, whatever is remaining is a union of annuli. You can just extend your map because union of annuli is nothing but homotopy between free homotopy between two curves. You can extend that map to the annuli and thus extending the whole map to the K1 prime. So you have to take care of certain things, and Goldman bracket would help you to will give you enough details so that you can actually extend and such that this boundary of K1 prime, G1 of boundary of K1 prime actually lies outside K. So this is an important property we need, and that will be given by the Goldman bracket. Okay, I think I don't have much time. So, and this is that was the base case. So you construct on K1 prime. So the next step is you have this K1, and then you have this connected components on this is on the domain, and also on the codomain you have a similar situation. So you would have to prove that all these connected components, the image of the fundamental group of these connected components will fall onto an image of the connected component on the right hand side. So that is the main technical lemma in the paper, and that we use some combinatorial group theory and again use properties of Goldman bracket to prove this, and thus we will extend the whole map step by step and to a map onto the whole surface, whole non-compact surface, and we also take care of the base points. And ultimately, the map we get would be proper, and it is so thus we have a proper map which is a homotopy equivalent, so it has to be homotopic to homeomorphism. So that is how the proof works. I hope I was able to explain it well. And then a slide. So this is a slide. This is a different way of stating the theorem, and it is a bit more general that if you have two non-compact surfaces without boundary, and if it is not homotopic, so wherever we are, so the main thing we are using in the proofs is this third point in the theorem. That is, if you have two free homotopy classes, so sorry, I sigma is a geometric intersection. Right? That is, you look at the intersection overall representatives and you take the infinite. So if the images have zero geometric intersection number if and only if the free images have zero geometric intersection number. If this property is preserved, then any homotopy equivalence would be homotopic to a homeomorphism. Right? So that is what this theorem is, and it also characterizes the image of Dane-Nielsen-Baer map. Dane-Nielsen-Baer map is basically what MCG plus. So the thing I wrote down in the beginning. This is the Dane-Nielsen-Baer map. F goes to F star. So in the case of infinite type surfaces, this characterizes the image. So what elements in out I1s would be generated by homeomorphisms, though would be induced by homeomorphisms. Those are the ones which preserve the Goldman bracket. Yeah. Thank you. I'll end it here. Yeah. So these are the references.
Thanks, Ajay, for the nice talk. Any questions? So why are you not considering the plane and the cylinder? Is that like the two?
So in the plane case, you have maps like Z going to Z square. So this is so anything. So this is not a homeomorphism because it has degree 2, but it is a homotopy equivalence. So you like in plane and in cylinder, you have very easy counter example.
Right.
Yeah.
And
Even
when
in the
you
case of
say,
cylinder, you have.
yeah, and when you say that you have a filling system and then you construct the subsurface which contains that, do you mean the minimal subsurface which contains that, or how do you prove it's
No,
unique?
no. I just need a surface which will contain all those free images. That's it. It could be as big as you want.
I
It
see.
doesn't need to be minimal. Yeah.
I see.
So
I see.
anything bigger than that would work.
Any
Yeah, I
other
wasn't
questions?
able to completely give all the details, but yeah, I just gave the.
Yeah, it's half an hour is very difficult. Yeah.
Mm.
Any other quick questions for Ajay? If not, let us thank the speaker.
Thanks.